Welcome to Thermodynamics-Screencast-1 for Chem 1B at Shasta College. Let's take a look at an example we worked on in class, the decomposition of calcium carbonate, and the delta H value and the delta S value were given, and we calculated the delta G value for this reaction at two different temperatures. At 25 degrees Celsius, the delta G was positive 129.9 kilojoules, so the reaction was not spontaneous at that temperature. And at 1000 degrees Celsius, the delta G was negative 26.5, so the reaction was spontaneous at that temperature. Now, what's the temperature at which the reaction goes from being spontaneous to not spontaneous? Well, the relationship for delta G in terms of delta H and T and delta S is this. And if delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous. So at 0, the reaction is going from spontaneous to not spontaneous, or vice versa. So let's solve delta H minus T delta S equals 0 and see what temperature we get. And if we solve for T, we get delta H over delta S. Delta H is 177.8 kilojoules. Delta S, let's convert that to kilojoules per Kelvin, so the units cancel. So it's 0.1605 kilojoules per Kelvin. And that works out to be 1108 Kelvin. Now, if we want to make this degrees Celsius, because we had done our previous temperatures in Celsius, that's 835 degrees Celsius. So that's the temperature at which this reaction changes from being spontaneous to not spontaneous, or not spontaneous to spontaneous, depending on which direction you are going. Now, one other thing to note, what does this mean? Well, if we look at this reaction, and note that its equilibrium constant is simply the pressure of CO2 at equilibrium, because calcium carbonate and calcium oxide are both solids, then if we track CO2 pressure, which is the equilibrium constant, versus temperature, you might want to think about what this should look like. And here it is. And notice the equilibrium constant is a very small number as the temperature, when the temperature is very low, because at low temperatures the reaction isn't spontaneous, so we don't expect there to be much pressure of CO2 at equilibrium. And it's not as if it hits 835 degrees Celsius and then suddenly the reaction goes. As the temperature increases, more and more and more reaction is occurring. It doesn't really start increasing significantly until it's getting somewhat close to 835 degrees Celsius. And at 835 degrees Celsius, the equilibrium constant is equal to 1. So we have kind of a balanced equation, or a balanced situation where we have reasonable amounts of products and reactants. And then as the temperature increases beyond 835 degrees Celsius, the pressure of CO2, which is the equilibrium constant, just simply gets bigger and bigger. Okay, let's do one other thing, revisit an example from class. This is the one with nitrogen and hydrogen and making ammonia gas. And the incorrect values for delta H and delta S were given, and so we had to kind of skip past that part. So this is just putting in the correct values for delta H and delta S and revisiting the problem. So for the reaction of nitrogen and hydrogen to make ammonia, delta H is negative 92.2 kilojoules, so the reaction's exothermic, and of course it is enthalpy favored. The delta S for this reaction is negative 198 joules per Kelvin, so that's a negative delta S, so the reaction is not entropy favored. And if we calculate delta G, or delta G naught, at 25 degrees Celsius, we get negative 33.2 kilojoules. That was the value that was given in class. That was correct, but the delta H and delta S hadn't been given in class. So here are the correct values. And then just revisit the interpretation. Since we calculated a delta G naught, or a delta G under standard conditions, What this means is, since it's a negative value at 25 degrees Celsius, the reaction above is spontaneous under standard conditions. And standard conditions for gases are 1 atmosphere. So this means if we start with 1 atmosphere of all the gases in this system, if we start with 1 atmosphere of each of those, then the reaction will go to the right, it's product favored, and it'll do that until it reaches equilibrium. It'll go to the right until there's more NH3 and less nitrogen and less hydrogen, and until equilibrium is reached. Now, suppose we do this reaction under non-standard conditions, and the amounts we used for our initial amounts in class were 0.1 atmosphere each of N2 and H2 and 1,000 atmospheres of NH3. And notice, if we start with very little N2 and H2 and lots of NH3, it's not too crazy to think that maybe the reaction won't go further to the right. It won't make more products. It might go to the left instead. Well, let's find out. And how we do this is we calculate delta G under non-standard conditions. It's equal to delta G under standard conditions plus RT log Q, where Q is the reaction quotient. Plugging in, as done in class, delta G standard is negative 33.2 kilojoules. R is the gas constant. Make sure you use the one in units of joules per Kelvin. T is the temperature in Kelvin. And then the log, natural log of the reaction quotient. In this case, we start with 1,000 atmospheres of NH3, and that's squared. We have 0.1 atmosphere of N2 to the first power and 0.1 atmosphere of H2 to the third power as our reactants and the things in the denominator of the reaction quotient. And when we calculate, we get plus 23.8 kilojoules. And what that means is, since that delta G is a positive value under these non-standard conditions, the reaction is not spontaneous. So the reaction won't make products under these non-standard conditions. And in fact, if it's not spontaneous to the right, it will be spontaneous to the left. So the reaction will go to the left, makes more N2, more H2, uses up NH3 until equilibrium is reached. And that's it for screencast number 1.